then we can actually do the statistical density functions and get them. So, let's see. Thank you. All right, so this is cross correlation in a nutshell. Same thing as auto. The only difference, and I'm going to point this out, they have x, y. X is the one that is not going to have the skew. So it's the first function, x of t, and it's going to be y of t plus tau. Tau is the skew, or the amount you're going to push something and then do this integral. Now, an estimate here, really, if it's a capital R, not a script R, that's in the statistical domain, assuming you would have an f of x and an f of y, but you don't usually have that. So it's almost always done in the time domain. Do you all remember with ergodic, the time domain autocorrelation function would have the same value as the statistical autocorrelation. It's called ergodic. This is, wide sense stationary signals don't have to be ergodic, but for all intents and purposes, we assume that. Now, the order is important, so if you take x, y, it means x is the non-skewed variable, y is going to be skewed. If it's y, x, y is the non-skewed, and x will have a skew, and they will be different, which is something you don't expect, because you remember with autocorrelation and with convolution, it doesn't matter which one goes first. With cross-correlation, it does. Just something to keep in mind. Now, these slides, there's only about 8 of them, and they just hit the points without going through a whole lot of discussion. And y'all follow me on this? Can I move along? Nothing big here other than keep in mind order is important. So now they do an example. I almost feel like doing this example. But when you have something like this, where you get a cosine 5t, in fact, we can probably just talk our way through this. There's a wrong, something wrong there. I think we pick it up. You don't need to turn the lights on. But here he has x is 2 cosine. So x of t is 2 times cosine. And he has 5t. I'll put 5t down here. Can you all see this, by the way, when I'm writing it? I'm just copying what he has. And then y of t is going to be what? 10, is it? 10 times the sine of 5t plus things. Same exact arguments, right? And he wants this estimated value. He wants actually autocorrelation function, and is it x versus xy of tau? Really what we're talking about is the expected value. This would be in the time domain of put x first, so we have 2 times cosine of 5t plus theta, and then it's going to be times 10, so I'm just going to make the 20 right here, 20 times cosine, and this is going to be a sine of 5t plus theta, and it's the expected value of that. And he said, 2 jointly wide sense stationary random product. Theta is uniformly distributed between 0 and 2 pi, which gives you the statistical nature of what we're talking about now. Okay, now with this one, the big deal is this. If we have cosine of A times times the sine of B, that's 1/2, and it would be times the sine of A plus B, and it's going to be plus the sine of A minus B. Now, I don't think he has that stated explicitly, but what he's doing is that. Now, see if you pick up the mistake here. Okay, so A and B are just these arguments right there. A would be 5t plus theta, B would be 5t plus theta, or A is B. Do y'all follow me, class? I'm just making sure everybody sees this, right? So when we take the sum of the two, A plus B, we should get this itself right here should become, let's put it right here without doing anything different. So So this should become the expected value of 1/2, and it should be cosine of 10t, and it's going to be plus 2 theta, and then plus, and then it should be simply, not cosine, sine, pardon me, sine, plus, and then it should be the sine of, and what I have to do, I didn't do this right here. This should be t plus tau and plus theta. I'm very sorry about that. I forgot to add the skew in here. So when you get that skew here, you're going to get, let me do it again. You're going to get the sine of 10t right here plus 2 theta, and then it's going to be plus 5 tau. Then down here, you're going to get a plus, the 1/2 would still be there, the sine of, and it would just be 5 tau here. What I'm really saying is this, right here, this should have a 10, 5. Can y'all see that? Because it should be 2 times 5 times t. There's 2 of those things. Won't matter though, and I'll just mention this. I put that up here only to really identify this as the identity. And some of you should have a natural question where we'll be given those identities. I'll give you some trig identities if you're going to need them. Like the last page of the final exam or the quiz, I would provide that information so you could look it up and see what's going on. A lot of times though, in the past, for me personally, when I've run into weird stuff like I got a cosine times the sine and I'm wondering about it, I'll just use Euler's identity. And I showed you how to use Euler's where you replace the sine or cosine by either e to the j omega theta plus e to the minus j omega theta over 2 if it's a cosine, or e to the j theta minus e to the minus j theta over 2j. Do the multiplied products and you can separate out usually the identity fairly easily. Now if it's cubed or higher, you get to spend some time at it, but it shouldn't be that tough with these things. Now looking at this thing, just looking at it, there's one particular thing that stands out. You see how this has no theta in it? So when you integrate that, you're integrating from 0 to 2 pi. Just something, it's not a function of theta, you just get 2 pi, and then you divide by 2 pi. Do you all follow me on this class? It's actually going to be 2 pi divided by, 20 divided by 2 pi times 2 pi divided by 1/2, or 10 times sine of 5 tau. That's what that value is there. The other one, and this is important you see this, on a test or a quiz, you have to be able to see this. If you look at this one right here, this part right here, you don't need to do anything more than look at it and say it's 0. Here's why. Remember, theta is uniformly distributed from 0 to 2 pi. You with me on this one? If you multiply it times 2, you get 2 periods right there instead of 1. Y'all with me? But you're going to integrate this function over a full period. Anytime you have a sine or a cosine integrated over a full period, it is 0. Y'all with me on this? Now, if it was sine squared, it wouldn't be, but sine, it would be. Y'all with me? And it's important you see that. Which means that part goes away, and that's the answer, and it is the answer on that one. Something I'm going to comment on too. Now, if that is the autocorrelation function, or sorry, cross-correlation function of those two, there's one thing that stands out in this one. Where's the maximum of this function right here? I really want to make this point. Is it at 0? Let me ask you this. Tau equals 0, is it a maximum or minimum? It's 0, right? You'll notice one other thing about this. This doesn't have to be strict positive like an autocorrelation kind of deal. You with me on this? Actually, autocorrelation doesn't have to be strict positive, but the Fourier transform does with an autocorrelation. This one, the sine, will not have a transform that's going to be strict positive. but it doesn't matter. This is cross, not auto. When you look at that though, you can see the maximum is skewed by what? 5 tau equals 90 degrees or pi over 2, right? It means tau would be pi over 2 divided by 5 or pi over 10 radians. So there's a relationship between x and y, but the skew is exactly, and by the way, every time you go a period, it would appear again, but you can see it's skewed by that 90 degrees, really. Pi over 2 divided by 5, so pi over 10 radians. That's where the peak is. And then it keeps appearing periodically all the way around. The reason that's important, in general, is if you know that, follow me on this? If you're watching a process and you know whenever the second process is going to be the value of the first process with a time lag. And if you see the first process hit a peak, I think of the stock market when I'm talking about this. And I always think about Intel chips and Dell computer values. Intel, now, I don't know if this is generally true now. I'm talking about 15, 20 years, actually 10 years ago. I don't know if I can get in trouble for saying this. Anyway, don't do what I'm telling. Anyway, what we did, a very bright guy named Sungil Kim, or I think I've told you about the guy that I worked with. We had a paper we published on using it, and it really was global optimization methods to predict future stock market values. And what we did is, this example, this is made up example for the record, wherever the phone is. Who's recording this? Oh, you are? Okay. Yeah, made up, complete fit. Anyway, when Intel came out with a new process, what are they on, an i7 now? Isn't that right? Anybody? You know what Intel is, right? All right, so when they came out with a new processor, all of a sudden all the new computers integrated in, and you had a next generation of computers that were sold. You've probably seen this with Lenovo and iPhones and stuff. There's always a new processor makes a new phone more appealing, it's faster. And the price goes up. So, and the stock goes up. So as soon as they came out with that, we knew the lag was about 3.5, 4 months, and stock prices of Dell computers would go up theoretically. Anyway, so what do? You buy a whole bunch of stock, if you believe this, when it's low. This is where this stuff makes money for you, if you know what you, not low, but not Intel stock, Dell stock, and immediately you put a sell order in for the estimated increase. And as soon as it hits that, you sell, and you make a profit. And that, I've done that for years ago. I mean, I would do stuff like that, and it was almost, it was like I was robbing people. I mean, that's exactly what they do on Wall Street, by the way. The problem is that 9/11 event, and all of a sudden all that goes to heck in a handbasket because it skews everything. But if things like that don't happen, you're usually pretty well off. And you guys are smart enough to figure this out. I had a student, God, I don't know how many years ago. This got to be over 20. And this kid was bright. I was teaching him EMAG and all this stuff. I don't think I taught him comp. But anyway, this kid is coming out of college, and he's recruited not by an electrical engineering firm of any type. It's by people on Wall Street that are hedge fund managers. These are people that, do you know what an actuarian is or anything like this? These are mathematicians that are very good at statistics that can predict what you need to charge for insurance in order to, based on statistics, to make money for your company. But you can't make too much because you go out of business because nobody will buy your insurance. So they're experts at this. Well, this kid had a mathematical mind, and he was recruited by these firms, and they pay a fortune for these, like 3 or 4 times. I don't know that for a fact. A lot more than you'd make as an engineer at that time. A lot more, a whole lot more. So he took the job in Wall Street. And after about 4 or 5 years, I get a call in my office. I said, well, he explains who he is. I said, well, where are you? Well, how you doing? Oh, I'm making a lot of money, but I hate my job. Hate my job was the key. He wanted to go to grad school. He wanted out. Basically, everything about what he was doing, as much money as he was making, he hated the job, and he wanted to go to grad school and do what he planned on in the first place. the moral of the story is don't chase the almighty dollar. You're going to find out. You're going to regret it if it's a job you really do. Seriously. Okay, back to this thing. That kind of power is what he was using, basically figuring out future values of something based on past values where there's a surefire relationship, and it's the correlation function. No point there. I tell you these stories only because when I was sitting there, I had professors that would tell me things that gave me a very clear idea of the things I didn't want to do and things I probably wanted to do. And I had some very interesting professors that had a lot of practical knowledge about things. All right, so with cross-correlation functions, there's one thing that is true. This first thing, the only thing you have to realize is when you have cross-correlation, regardless of the order, the value of that function, when there is no skew, you see the tau is 0 in this one, doesn't matter if y or x goes first, will always be the same. The fact is, if you have no skew, you're calculating the exact same quantity. It's just what? Well, it's honestly, you're going to find this out, but it's basically the square root of ry at 0 times rx at 0 with no skew. You'll see this in a second. Now, these things, this is true though, that anytime you have a cross-correlation function, it is symmetric or an even function. You can call it even. Does everybody understand what I mean? When I say even, what it means? So you can, right off the bat, if you see a cross-correlation function that is not going to be an even but an odd function, you know that that's impossible. Or I should say, for the negative values, you know it's impossible. I got to say one more thing about this. See this thing right here? Now this function itself should have a magnitude of tau right there. He doesn't. I'm just telling you that. I'm not worried about that right now because the value of tau is going to be, they're going to take it assuming it's strict positive, 0 or greater than 1. All right, the next thing is this, that if you look at the minimum or the maximum value at, if you take a look at this, rxy of tau is always less than or equal to the square root of the product of rx at 0 and ry at 0. Always. Now that's the mean squared, the square root of the mean squared values of those two. And finally, if the two random processes are independent, and this is important also, I'm just pointing out what's important to note. Then if you want rxy of tau, if they are statistically independent, it's just the mean value of x times the mean value of y. And if either one's 0, then you know it's 0, which is nice. All right, so this is something I know about. This is radar. And if you look at this, this is actually not too bad. There's something that's not quite right about it, but if you take a look at radar, what they really do is they have a short duration, very high frequency pulse. You see this first part? Can you all see what I'm pointing right there? That may only have, it may have like 10,000 cycles, something. You have to have enough cycles so you develop a carrier that will transmit the signal off your antenna. Remember, if you just have 3 or 4 cycles and you drive an antenna with that, it doesn't see a constant frequency. It sees an incredible bandwidth and very little power would be radiated. So you have to have this has to have about, right here, about probably, I don't have a clear proof on this, but it's doable if you take a look at this. If you take this function, if you try to make this function, what would be, how would you create it? Let me do it over here real quick. Don't worry about the lights, but I want to make sure you see this little aspect of what I'm talking about. Think of what was sent. Any ideas how you would mathematically create that function, not with electrons? Well, we need a high frequency carrier. Do you all agree with that? So you start with a function, and I'm just going to say x high frequency of t is going to be some a cosine of omega t. And here omega is 2 pi f, and call it F naught, omega naught, and call F naught of the order of 10 to the 9th hertz. That's gigahertz. With me? So I got a constant frequency, high frequency, and now I want to do something. I want to make it only a small portion of that to actually be created and launched. Mathematically, we multiply it by a pulse function, p tau of t. Remember, p tau of t is basically the rect function that has the argument t over tau. Y'all with me on this class? You've all seen rect functions, right? The only thing it is this. If this is the time domain, it has a value of 1 from minus tau over 2 to tau over 2, or another way to say it, it's centered at 0, the width is tau. That's it, right? So I'm going to multiply it by this. Now, what does the Fourier transform of that look like? It's important that you get an appreciation of the frequency domain about what's really happening. Can you put those lights on just for a second? I want to make sure this is important because you're going to see this being used when we get the spectral density functions. Well, what does it look like? Let's try this approach. If I have any function, I'll use x, h, and d. If I have x, no, I can't use x, h. Say I have f of t, and I know that goes to f of omega. It's a known transform. Follow me on this? Like if it was e to the minus at u of t, that would be 1 over a plus j omega. Everybody with me on this? A known transform. Now, if you multiply that by cosine, and I'll use omega t, that's called the modulation property. Do you all remember this from signals and systems? Do you remember it? I'm asking an honest question. I just want to know. Have you heard modulation, right? There is amplitude and frequency. This is amplitude modulation. If you look, the amplitude of this carrier right here is, quote, modulated. It is only going to have a value of the cosine waveform over a limited width. Otherwise, it's 0, so amplitude modulated. If it was frequency modulated, it would be omega naught plus something times t, and that something is a function of time, so the frequency would actually shift that you're transmitting. Can you all follow me on that? This actually has a transform of 1/2. I think you know this though. And now it's going to be times f of omega plus omega naught plus f of omega minus omega naught. Now the reason I'm saying it that way is, if I know this transform, then I simply take that transform, whatever it is, and I push it and center it at minus omega naught and plus omega naught. Everybody with me? I'm going to do this example, make sure it's clear to everybody. Back to this thing so you understand why you have to have a lot of cycles to transmit this. And I'm doing it over here because I want to leave that up. We missed 2, 4, 6. We're missing Jackson, isn't he? We're missing? Yeah, I think so. All right. Back to this thing. So I take my pulse function. I did this last class. Do you remember what the transform of that is? Sinc. Very good. It's going to be tau times the sinc of omega tau over 2. Correct, class? Now, I've got this. So I have, you might say I have my f of t right here. And I have my f of omega. Now, when I take that pulse function, I'll get out of your way in a second, and I multiply it times my high frequency cosine omega t, now what happens is I get 1/2 tau, and then I get that sinc function, Sinc of quantity omega plus omega naught tau over 2 plus the sinc function of omega minus omega naught quantity tau over 2. Everybody follow me on this one. I'm just literally doing what I showed you the transform is. I'm mathematically showing you the nature of this. And now the logical question is, what does that look like in the frequency domain? Or this should be a question. And you can see you've just got a sinc function, and you've got it centered at 2 different points in the frequency axis. So let me go over here, and I'll just show you what this looks like. If this is going to be the transform of this whole thing, and I'll call this F, wait a second, I gotta call this one right here, F of X of omega, so it is the transform of that short duration waveform. Out here at minus omega naught and here at omega naught, I center 2 functions, and both of them have the same height to start with, and they look like this. Now I'm just drawing, that's the sinc waveform. Are you with me, class? Now this part is important. You see the width of this thing right here? The shorter the duration of that pulse waveform, the wider it is in the frequency domain. As a matter of fact, as a pulse waveform's width goes to 0, you get an impulse function, and then it's flat in the frequency domain. Are you with me, class? This is real important to see. But the longer the duration of this pulse function right here, in other words, the more cycles it actually has in that waveform, like 10,000, 100,000, stuff like this, the narrower. And what actually happens in the real world, because of the nature of this, this may be of the order of 10 to the minus third, 10 to the minus 4 seconds. Milliseconds to hundreds of microseconds, with me? That means 1 over that has a frequency range of roughly 10 to the third, 10 to the fourth hertz. Got that? Basically. This is going to have a frequency range of gigahertz. It's 10 to this, basically 1,000,000 times higher in frequency. Now, if you let that duration go, so you get like 10,000 cycles, then instead of looking like this in a frequency domain, it looks like this. Basically, you're going to have a spike. And that means the frequency that you're actually transmitting, the majority of the power, is over a very narrow range of frequencies. So your antenna that is designed to transmit at, say, 6 gigahertz or something like this, 10 gigahertz, it will launch all that. Even though there's a slight variation in the actual frequency components, it'll launch it. If you get something that's real broad, broadband kind of signal, say you only have 100 cycles, then your efficiency, your antenna is almost kaput. It's just junk. You can't launch anything. The directivity is gone, everything like that. Remember what I'm telling you. So basically, they send this pulse, and you listen. Basically, you transmit, and you listen. You got to do this a whole lot of times, by the way, and you listen. And as you listen, this comes back. By the way, the order of magnitude of this is going to be anywhere from 6 orders of magnitude less to 12 to 14 orders of magnitude less. That's how much of a difference there is, because with radar, the total decay of the signal is proportional to 1 over r to the 4th. And also, the cross-sectional density of the target that scatters it is directly proportional to the amount you get. If you send out like a megawatt, you might get back maybe 100 microwatts peak power. That's the level of the amount, the magnitude of reduction. It can be a lot more than that. So now I've captured this, and here's what really goes on. He's showing you the high frequency component in this. The truth is, they strip that out. What happens is, when we take a look at the low, after we capture this signal and we do some processing, we just get a square there, basically. We get a rectangle. Something that has none of this going on here. And we can do this with modern digital processing. Then we take that and we simply do a cross correlation. In his, he does it at the high frequency. They can do it this way. It's very hard. It's called digitally defined radar, where they literally take the signal as it's coming into the antenna, receiving, reflected back from the target. They'll amplify it to a certain point, and they'll go right from A to D. They won't strip off the high frequency carrier, which is, in my opinion, kind of stupid, because that's the thing you want to get rid of. And you can do it with digital processing, and then they do a fast correlator. So here's what they got. Now they correlate these two signals, and this comes out. Can you all see? And by the way, this is not an exaggeration. You'll get something where this line won't even show up, and they'll get a very clear peak, and that peak has to do with the total round trip time. So it's associated with 2R. Can you all follow me? If you wanted to graph the actual distance on this axis, what you would do is say that value tau has to do with the round trip time. I'll just put it here, and I'll mention. So I know 2 tau has to do, has to do with the round trip time. So I went, and actually I went 2R. R would be the distance to the target. Does this make sense to everybody? Right, I went out and back. If R is the distance to the target, I had to go out, hit it, come back. Well, how fast is it how fast is it moving? It's moving C. I should have put that there. Speed of light times the delay time would be 2R. And that means R itself, or the range to the target, right here, would be equal to C tau over 2. Obviously, this is my area, so I'll spend a little more time talking about it, but I want to show you the applications. So if I send this and I listen, has to be something where I'm listening at a specific frequency range, by the way, because you know, in the real world, if you just listen for everything in the frequency domain, you're going to get crap that'll just saturate everything. You'll never be able to see anything. So what we're really talking about is something that would be a frequency limited, and you'd be looking only at a certain azimuth and elevation in terms of an angle that you're looking at. And you get this, but you would get a return in the raw data that's like this, and you can easily imagine extracting a value to range to target. Has anybody ever seen these old, like World War II movies, where they'll have a green CRT, and they'll have a little bar that looks like a second hand on a watch moving around, and whenever there's a target, there's a phosphorus glow. Y'all remember those? How many have seen these before? No? If you haven't, I wish you would take a look at this, because this is important. So what they're really doing on that thing is they're simply showing you at a given angle where the thing's transmitting. That has to do with this thing sweeping around. It's just the 2D radar. It's only looking around the feed plane or the XY axis. Whenever they hit something, this is for navigational radars, and they get a return, they can calculate using that calculation. They find the time delay, they find the range, and then they go out there and they put what they call a spot. So instead of a straight line like this, they're going to have that spot stop for a second, maybe, I don't know, a millisecond at that point, and the phosphorus will glow white. If you've ever looked at this, you'll see this faded green line kind of moving around, and then boom. Now, I was in an aircraft carrier, Eisenhower, in '87. I remember being on, it's called the flag bridge. An admiral will sit beneath the actual bridge, the captain's telescope, and he'll have these radars. And I looked at the World War II legacy radars, the SPS 49, 48. These are navigational 3D radars, and I was amazed. Like, I've never seen a phosphorus screen used to show radar at that time. Everything, I mean, a different way of actually showing or rendering the information. But I looked, and sure enough, and you could take a little cursor and mechanically scroll it out to that point, and we give you in nautical miles how far away it was, and it was very accurate. Have you ever seen this stuff? You're nodding your head. Have you been on a carrier or any?
No, not been on a carrier, but I've watched some of the, like,
videos?
watched the movies and seen some of the videos.
When you actually get out there and do it, it's kind of interesting, because I can see the ships from that. They can't be 100 miles away, but I mean, I can see things, and I'm always curious how far away they're. And I'll tell you one other thing off of, I mean, it has nothing to do with this, visual perception in the sea, especially when you're up there, the distances are skewed like you wouldn't believe. What I thought was maybe a mile, 2 miles, it's like 12 miles away. Anybody ever experienced this crap in the ocean? Were you in a big boat or a big ship when you had that or not?
It was pretty big. It was a big ship, yeah.
I can't imagine, I mean, really, I was amazed how wrong I was, because I can look over to, you know, if I look from here to either Haley or Fort Union, what do you think? Maybe 150 yards? I think I can do. When you get into miles, remember, your eyes triangulate, you got no triangulation. The only thing you're doing is in your mind scale, and you don't realize how big these ships are. When they're tankers and stuff, they look like dinky little things. I was completely wrong. Anyway, that's enough on that story. So remember this about radar, and if I had to bet, I got no way to prove this, I would bet at least 30% of the people in this class are gonna work in the defense industry. At least. This is my opinion. I've seen it too many times. And of those people that work in defense, about half of them are gonna be dealing with radar, especially adaptive radar. It's really come a long way. And I mean, you're gonna work in power industry is big, defense is big, and then microelectronics, you'd fly to California probably and work in Silicon Valley. Those are the three areas I see almost 85, 90% of the students going. How many are gonna go into power or are in power? All right, how many defense are related industries in Huntsville or any place? Nobody yet? All right, how many microelectronics, solid state? No. Wi-Fi? One. Well, this is news. I learned something. All right. Back to this application of radar. I'm going to just move through this. So when you send a signal XFD, it's pristine. It's exactly what you want. You shape that signal and launched it. What comes back is anything but what you want, except there's a component of what you send. So you get some scale factor A, and that's usually 10 to the minus 6 or less, something like 1/1,000,000th, 1 billionth, the actual value of the signal strength, not E field, but power density. And you get noise. And noise is something you like in a way because it's wide sense stationary and it's wide band. And you can get rid of it. I won't spend a whole lot of time on this, but here's how we really get rid of it. See this picture right here of the return? Now I'm going to send that pulse a whole bunch of times. Send it, listen. Send it, listen. Send it, listen. It's repetitive. In all those listening states, I take them and I go from an analog to a digital values and I store them. So I can store first, second, third, fourth, fifth. And I have that exact record. Does everybody follow me on this? I know from the time I transmit to the time I receive this, or basically I start recording everything I receive over a portion of time. Then I take all those signals that are A to D and I add them up. And guess what? Or the signal will add constructively and the noise doesn't add at all. That's the beautiful thing. You'll get rid of the noise by doing something called coherent signal processing. And that's all it means. You're going to see mathematical definitions that'll drive you out of your mind on that. But they're literally taking a snippet of this recorded signal, go A to D. Do the same thing, snippet of this, A to D. Same thing, and they'll get 100 of these things, they'll add them together to get rid of the noise. And that's how they can see things that in the real world, when you get radar returns, this doesn't exist. You see nothing but noise. You can't see that. But after, for a lot of applications, you can't see. When you add them up, bang, there's the target, and you can see it clearly. That's called coherent signal processing, but it is based on this cross correlator. All right. So anyway, they transmit a signal. Now I'm going to cut through. I want to cut to the chase on this. I'm yakking about this a little because it's so important in the long run for some of the stuff you're going to do. This whole class is meant to be an applications class, and that's the reason I'm trying to show you things where I personally have applied this theory to, and I've got results. So when we do a cross correlation function related to signal processing and a radar signal, after all is said and done, the noise, when you have the correlation between the noise, see how you do this crap and you're basically going to get an autocorrelation right here. Noise, see x of t n of t plus tau. That function is gone. It doesn't exist. Remember, the mean value of noise is 0. Do you remember I said if the two things are statistically independent, then the auto or the cross correlation is really x bar times y bar? Well, if the noise, call it n bar, is 0, 0 mean, you get 0. This goes away, and you get this, and this is the beautiful thing. So we can get rid of the noise by doing this cross correlator, and then we do 6.71. Okay, you can shut that off. What is our final battle?
Thursday.
What's our final name then?
Also Thursday in the afternoon, I think.
Farouk. How many are in both classes?
And then Jackson's in it too.
What's that?
Jackson's in
Jackson? Well, for what it's worth, you can bring food in here as long as it doesn't put crunchy stuff and some coffee or whatever you drink, tea. These energy drinks that I see here. Used to be Starbucks, now they see cans of Red Bull or something like that, Monster. Okay. Oh,
It's like.
reading it.
Out of order.
Don't worry about it.
Two independent stationary random processes having sample functions x of t and y of t have
The key word there is independent. They're not correlated. Follow me? Statistically independent would be. Does he say statistically independent? No.
just
All right. Well, go ahead.
have autocorrelation functions of r x of tau is 25 e to the negative 10 magnitude
E
tau.
to the minus 10,
Yes,
magnitude of tau.
yes, sir.
Tau
Co-
squared or tau?
Tau. Cosine 100 pi tau. And ry tau is equal to
Okay.
16 times sine of 50 pi tau
50 pi tau? Go ahead.
over 50 pi tau.
I'm going to suggest one thing. See this function? That looks like a sine x over x. Do you all see that? Take 50 pi tau, make it equal to x. Sine x over x is a... So this really looks like 16 times the sinc of 50 pi tau. Now, you don't have to do it this way. I'm just pointing out something. So I got x and y. Now what does he want? A function z, I'm going to call it z of t, is equal to x of t plus y of t, right?
Yes.
We're not going to do all the parts of this. They're mathematically irritating because there's a lot of things going on. But I want to do this one. So he asks what? The autocorrelation function of x of t, or cross correlation, or is it auto? Auto?
Auto.
Autocorrelation function of this function. He doesn't state it this way. He just puts x of t plus y of t. He wants the autocorrelation function. Call it z of t, so you're clear about it. You with me? Now, I would suggest you do it this way. Mathematically, just state what the definition is of the autocorrelation. So, r z of tau is really the expected value of, and here it would be z of tau, or z of t, pardon me, z of t times z of t plus tau. Now, I don't think he says it's ergodic in there, but it's assumed ergodic, and it's assumed wide sense stationary. We don't need the ergodic per se, but the nice thing is if it's ergodic, we can use time domain averages as statistical averages, or as that density functions average. Or can you understand that, class? Don't make a big deal out of it, just appreciate it. We're gonna get away with everything on this one if we can. Now you simply put, in terms of z, put x and y. So what I need is, and I'm gonna ask you about this, because this will be on probably your quiz and on the final exam. So here is gonna be the, now I'm gonna put it as the expected value of, and now for z of t, I just put x of t plus y of t, and then I multiply it by x of t plus tau plus y of t plus tau. And now I do the math. Can you all follow me? I'm literally just taking the definition, and now I'm going to expand this. So when I do this, I find my r z of tau, this is part A of it, is going to be the expected value of x of t times x of t plus tau, plus, and then it's going to be y, I'm taking the last, y of t, y of t plus tau, you know, y, plus, and then I'm going to take the crossings, so it's going to be y of t times x of t plus tau plus x of t plus tau, or I mean plus x of t times y of t plus tau. Everybody with me on this class? I want to make sure you understand just the definition, and I'm simply going through, turning the crank, as they say, going through the motions to get it down to expected values. Now, if you look at this, some things become evident, I think. What's the expected value of this? It's the definition of the autocorrelation function, isn't it, of x. Can you all see that? First, how many can see this? If you can't see it, I need to make it, Riley, you sit in the far back. For the life of me, I mean, you're free to do that, but I don't,
I
makes,
got your late as well.
huh?
I got your late, so I just said that.
No, you can move up, don't worry about it, it's not small, you're not gonna irritate me. I mean, if it helps. I don't tell people where to sit, but in those big rooms, I have kids at the far back, I don't know how they see what I'm writing, because I use the board. Okay, so now I'm just gonna break it down. This RZ of tau would be equal, that would be the autocorrelation, you're right. It would be Rx of tau. Does everybody agree with this part, right? Let me get the next part. What is this? The expected value of y of t times y of t plus tau is? Right, autocorrelation, which happens to be, well, just put it down, plus autocorrelation y of tau. Now, the next part is important. These, I mean, that's this and this. We've checked this one off and this one off. But what about this one? The key thing is they are statistically independent. Correct, class? Back there? All right. That means if I have statistical independence, Rx, I'm sorry. If I have the estimated value or cross correlation of x, let me do it this way. The expected value of x of t times y of t plus tau, or vice versa, is just equal to the expected value of x times the expected value of y. Do y'all follow me on this, class? Expected value. This is the important part. By the way, so this is going to be the next term, which is right here, would be plus x bar y bar. Can everybody see how that would occur? Because they're statistically independent, that's the reason. What about the next bar here? Isn't that the same thing? The skew means nothing. So it's 2 times x bar, y bar. Now, I'm not done. Now look at these things. Look at this one. Do you remember how you calculate? If this is the autocorrelation function, do you remember how we calculate the mean? How do you get the mean squared value? This is the autocorrelation function of x. Mean squared value of x is?
Tau equal to 0.
Say, yeah.
Tau equal.
He's right. You put tau equal to 0, and what that is, by definition, is just the mean squared value of x squared of t, right? That is mean squared value. But if we wanted the average value, what do we do?
Tau goes to infinity.
As tau goes to infinity, it would go to x bar squared, right? But what happens as tau goes to infinity to this?
0, 0.
Goes to 0. Y'all see this, class? E to the minus 10 tau. As tau goes to, it goes to 0. I don't care about the cosine. I don't care about anything else because that drives it to 0. Which means this goes away. Can y'all see that? All right. So, just tell me if I'm right about this. For Jerry, if I look at r of my z, and he calls it x plus y, I don't care what you call it. That's just going to be the first function, which is 25, and it's e to the minus 10 times the magnitude of tau times the cosine of 100 pi t plus 16 times the sinc of 50 pi t, or tau. Jagger, is that right? Part A. Is it right?
Just Rx of tau was not y of tau. And then J plus that. He didn't convert it to the same function.
I don't care. That's, do y'all follow me on this? Now, one question, just looking at this. If you look at this, can you all see there's one particular thing that doesn't go to 0? Well, it does go to 0, I'm sorry. But lingers, that's the word I should use. This thing is damping down, it's going plus minus, and asymptotically approaching 0. Can you all see that? But this thing is getting killed quick. Either minus 10 tau, it's gone in a hurry, just to be clear about it. I'm not going to ask you to sketch a function like this, but I would ask you to sketch something like this by itself. Just be aware of that. It's a sinc function. You should know how to sketch that, or the magnitude of the sinc function. And part B is what?
X at t minus y at t.
All right, now, listen, you don't have to write anything. I want you to just listen. It's this easy to see. If this is a minus right here, y'all with me? I'm just changing one thing right here. That is my z. Now, here, does it change here? Here, it changes, right? I want you to just see this. Don't worry about writing it down. I'm just changing what I've had available to change. Now, you don't have a whiteboard in your notes. Well, maybe you do now that I think about it. If you're taking notes on these pads and stuff, you probably can you just copy and paste like a section, which is nice. All right. Now you see, that's all I did, right? Now watch. This term times this term is still this term. Can you all see this? And this term times that term is still this term. You all see this? Now, this times this just makes this negative and this negative. Everybody with me on that? Ain't gonna affect beams though. Why? Because down here, this would be negative, but it's 0 anyway. Plus or minus 0 is 0. Which means it's the same thing. Jared, check and see if B is the same as this. I think it is, but I don't remember. Y'all with me? It's nice to see these things so you don't have to go through all that math again. All right, what's the third? I don't remember.
Both cross correlation functions.
All right, now this is, the way he says it doesn't make sense. Here's what he's saying. He's gonna take, now we're gonna cross correlate, call it Z1 of t equals x of t plus y of t. Remember that one? And he's gonna say Z2, this is like taking parts A and B. Z2 of t is gonna be x of t minus y of t. Y'all with me? Now he wants to correlate those two signals. All right, so now it's almost not worthy to pursue, but you can see what's gonna happen. If I want that, or I want the expected value of, and I'll call this R Z1, Z2, it's the expected value of x of t plus y of t times, and now I'm going to do the skew on this one, x of t plus tau minus y of t plus tau. Can you all follow me? This is the first function. You don't put the tau in there. That's it. The second function here, you got to skew the argument t plus tau. I use the word skew. It just means you're adding tau to the t argument. Now, if you look at this, what happens? Some of you will see this in a heartbeat. I can see that this is going to be the expected value of, well, let me just talk my way through this. Can you see I'm going to have x of t times x of t plus tau? Can everybody see that? Ryan, can you see it better? That's just r, what? That is rx of tau, right? So that checks this times this. Everybody with me? Now, pay attention. The y of t times this, that's minus the autocorrelation of y. Can everybody see that? So it's going to be minus ry of tau. Now we get into the cross terms. What about this times this? Y of t times x of t plus tau. The expected value of this would be the mean value of x, mean value of y, right? Which is 0. How about x of t times minus y of t plus tau? Expected value? 0. In other words, this is the answer, or said differently, you tell me if I'm right, Jer, or Jagger, right here makes that minus. So this would be C, and this would be R of, I call it Z1 comma Z2. Isn't that it? Take a look, make sure. Now he has a lot, if I'm not mistaken, he has a whole lot of crap there.
He has plus 16,
He made a mistake.
Oh, okay.
I'm pretty sure.
Yeah, I mean, because he has R.
He has a minus earlier.
Yeah, he
the
does.
minus just disappears.
He must have messed it
I'm
up.
glad you worked that one. But there are subtle mistakes in the solutions manual. I don't, can you, Jared, make a note. Do you have a pen? Give him a pen to make a notation. Just, I want to make sure, I'm trying to correct that thing. And I'll copy the whole thing again for the next one. All right. What's the next
You
one?
may just scribble out the box so that you like.
Yeah, yeah. What's the next one?
The autocorrelation function of x of t times y of t.
Auto correlation of x of t times y. Just think about this. So now I'm going to have a z of t. Just think about this. My z of t is now x of t times y of t. And he wants the autocorrelation on it. So if I want that r z of tau, I'm just going to do the definition. It's going to be the expected value of, you take that, leave it alone, x of t, y of t, right? And it's going to be times x of t plus tau, y of t plus tau. This is getting interesting. I think this is the one that's mathematically wrong. I don't remember if that's true. So what is that gonna be? Well, this is one big multiplied product, right? So I'm gonna have the expected value of x of t plus tau, y of t plus tau. Do you agree with this? And what is that gonna be? I'm asking a question here, but I'm not sure how he does this one. Go over here. So, I'll try to say this in a way that's intelligent. If I look at this, isn't this the expected value of x of t plus tau times the expected value of y of t times y of t plus tau? First, do you agree with that? That expectation operator, right, would move through that product. And the reason I can do this is independent of that. Do you agree with that? In the back of the room, can you see it? Do you agree? I don't know how he does it. Because you can mess around with this and do some pretty wacky things if you want. But what is this?
Or x of tau.
It's Rx of tau, isn't it? What is this? Y'all have, you see, we kind of multiply those two things together. I don't care to, you can multiply them and expand them. I don't remember what he does at this point, but does he have that answer?
Yes.
All right, now that is an irritating one, and here's why, in my opinion. You've never been thrown a problem where you got a product there. And that's where you gotta almost work through it. Now, if they were, I wanna be clear about this, if they weren't statistically independent, what I did here wouldn't work. You'd also have to have a correlation coefficient that works into this, all right? But that would be a messy problem, especially if you're looking for a closed form solution. But this is the way you would do the problem. And it exposes a lot of the aspects of what you need to do. In other words, recognize statistical independence means the expected value of one thing times the expected value of the other thing is fine to do. You can break it up that way. Did you have a question? All right. That's a good problem. There are a couple other problems in that section I'll give you. I think that's the only one I assigned, right? But I don't know if you noticed it, that part's tricky to see it. And I can imagine some people on a quiz or test would have a problem. Last thing I'm going to cover, and I know my time is about over, I want to mention spectral energy density, and this did I put on OneNote, the spectral energy density stuff, and it's in chapter 7. This is real important. Matter of fact, this is, in the course, this is probably one of the most important topics. I don't have time to prove this, but in his book, or in the PDF, he proves this. But if you have a function, any function at all, if you have like x of t and the Fourier transform of that is going to be some x of omega, then there's a relationship that if this is a time-limited signal or an energy signal, then you notice that the integral from minus infinity to infinity of the magnitude of x of t squared dt will actually be equal to the integral of 1 over 2 pi, the integral from minus infinity to infinity, of x of omega squared, and then it's going to be d omega. Do you remember this at all from, it's Parsifal's theorem? Have you ever heard it? Did you tell me about that you heard about it, Elijah? I mean, it's in your, do you remember hearing something like that, Parsifal? Now what it's really saying is if we have either x of t, we know the value squared, we can integrate this, that would be the energy in a signal. If you think of that x of t like a voltage in a 1 ohm resistor, this would be the energy dissipated in a 1 ohm resistor. Think of it that way. assuming it's a time limited or time domain signal that has finite energy. This would be the Fourier transform of that, and if you do that mathematical operation, you'll get the energy too. This is important. Now, if we have a function, an autocorrelation function, an autocorrelation function is something, if you think about it, autocorrelation function when tau equals 0 is it the actual x of t squared, isn't it, class? So, if you have the autocorrelation function, let me just do it this way, of tau, and you have the Fourier transform of this, we'll call this, and this cap of x of omega. And so I'm going to have, this is called the spectral density function, and I'm going to do it with omega. I'm assuming if I have this, I can take the Fourier transform, I have this. You all with me, class? The way you would do it is actually you would say S x of omega would be equal to the integral from minus infinity to infinity, and it would be r x of tau times e to the minus j omega tau d tau. You wouldn't do it with t, you'd do it with tau, because it's the argument of autocorrelation. You don't need to do that, you need to use tables. Mathematically, you can do it if you want to, but don't mathematically need to do it for most things. So if that's the case, and I wanted the energy or power, depending, because with power signals it gets a little different, but the essence is the same thing. If I had something like I gave you a spectral density function, give me 1 second. I'm going to say also if we had Rx of tau, and instead of the omega domain, we had xs, xx, s of x of f, in other words, frequency, not omega, 2 pi f would be omega. In either case, if we wanted to know the amount of energy, or power, we would say the only thing we need to do is take the integral of x, s sub x of f df over the range from minus infinity to infinity. That will give you the amount of power or energy, depends if it's a power signal or an energy signal, or you can take 1 over 2 pi, the integral from minus infinity to infinity of f of x of omega, d omega. Now, I know I'm moving on this one, but I just want to do one last thing to show you how easy it is. So let's assume we have that spectral energy density. The units of that are usually volts squared. All right, volts squared per hertz. This is in chapter 7. And exercise 7-2.1. I know I'm holding, just bear with me for another minute. I think, didn't I put that exercise up on there? All right, now watch, this is how simple it is. So here's what he does. He says S, X of, isn't it F on this one?
Yes.
And that's equal to 10, and that's true for F, magnitude of F greater than, what is it, A less than B, and 0 else?
Yes, sir.
All right. So what it's really saying, if this is the frequency domain, and this is Sx of f, this has to be strict positive. He's going to say it's 10 between A and B. I'm going to put A here, B here, it's just 10. Now that is, for all intents and purposes, think of it as the power, it's volts squared per hertz, but really think of it as the power density. Just think of it that way. You're going to have the same thing down here from minus B to minus A here, you're going to have the same thing. The height of this would be 10. And what's his wording on this one, Elijah? He asked for what?
Find the mean square value of the process if A equals 4 and B equals 5.
All right, the mean squared value of the process would be the power, or the total, the integral of S of them. Basically, it's this. He doesn't say it exactly that way, the mean squared value of the process. Well, the process is typically a voltage for electrical engineering. So this, I'll call it the mean squared value. That would be equal to 2 times the integral. And what's A and B in this one?
A is 4, B is 5.
All right, so it's from 4 to 5 of 10 df. And by the way, I put a 2 there because whatever happens here is identical to what happens here in terms of the area under the curve. Y'all with me? I do that and I see I get 20, don't I? I get 10 from 4 to 5 is just 10 times 2 is 20. Isn't that one of the answers?
Yes.
It's that easy. Y'all with me? Now, the next thing is he just does this. He says, now this process just goes like this. It goes from, is it 5 or 10?
It's 0 to 5.
Yeah, but it's symmetric, right? From minus 5 to 5, it's got a height of 10, right? And this is my S, X of F. Can y'all follow me? If I ask for the mean square value of the process with this transform, what is it? 10 times 10 is 100, right? It would be 100. Do y'all follow me on this? It's just the area under that curve. Is that the right answer?
Yes.
Can you all see how simple this is? Now, the tricky part is, what if he asks you for the autocorrelation function? Now you'd have to take the inverse transform. I'll do a little bit about that on Friday. I don't want to make this thing overwhelming. I'm not going to quiz you on this on Friday. The prior stuff I will quiz you on. Y'all with me on this class? And I'll finish it up there. But I needed to do this, and I tried to make a big spiel about the radar thing, I know. But the reason I did is because I think some of you got to do the radar field. I mean, I could be out of this class. It's small, but. Now, is anybody graduating this summer? I'm asking for a reason. It's graduation. What they always hit me up with is they want the graduating students' grades ASAP kind of deal. And that means I'll grade yours, not the grade